Hello everyone. Welcome to the second lecture of data structures and algorithms. In our previous lecture, we discussed the basic idea of a data structure. But now, let's think about an interesting question. Are all data structures the same? Well, the answer is definitely not. Just like vehicles can be classified into cars, bikes, buses, and trucks, data structures can also be classified based on the way they are organized and how they use memory. In today's lecture, we are going to explore two important classifications. First, we will understand static and dynamic data structures. And then we will move on to linear and non-linear data structures. Don't worry, we'll understand each of these concepts with simple examples. So, by the end of this lecture, you will have a clear understanding of how different data structures are categorized. Before we classify data structures, let's quickly remind ourselves what exactly is a data structure. Imagine you have the marks of 5 students, 75, 82, 68, 91, and 85. If I simply write these numbers randomly, they are just raw data. But when I organize them in an array, suddenly it becomes much easier to access, search, update, or sort them. So, a data structure is basically a systematic way of organizing and managing data so that we can perform operations efficiently. And this is the complete journey. Data yields, organization yields, operations yields, efficient solution. The way we organize data directly affects how efficiently we can solve a problem. Now let's understand another important term, data type. A data type tells us two things: what kind of value can be stored and what operations can be performed on that value. For example, if I want to store someone's age, I can use an integer. If I want to store a decimal value, I can use float or double. For a single character, we use char, and for true or false conditions, we use boolean. Think of data types as the basic building blocks of programming. And just like bricks are used to build a house, these primitive data types are later used to build more complex data structures. Now, let's understand another important term, data type. A data type tells the computer what kind of value we want to store and what operations can be performed on that value. For example, if we want to store a student's roll number, we can use an int. For decimal values, we use float or double. For a single character, we use char, and for true or false, we use boolean. Now, data types can be broadly divided into two categories, primitive and non-primitive. Primitive types such as integer, float, character, and boolean are the basic building blocks and usually store a single value. Non-primitive types such as arrays, linked lists, stacks, queues, trees, and graphs help us organize multiple values and represent more complex relationships. Think of primitive types as individual bricks. When we combine those bricks, we can build larger structures. And that's exactly where our journey into data structures begins. Now we come to the main topic of today's lecture, classification of data structures. We can broadly classify data structures in two major ways. The first classification is based on memory allocation. Here, we have static data structures and dynamic data structures. The second classification is based on how the elements are organized. Here, we have linear data structures and non-linear data structures. For example, arrays are generally static and linear, linked lists are dynamic and linear, trees and graphs are examples of non-linear structures. So remember, one classification tells us about memory behavior, while the other tells us about the structural organization of data. Let's start with static data structures. The main idea is very simple, their size is fixed. Memory is allocated before the program actually starts executing, and once the size is decided, it generally cannot grow or shrink during execution. The most common example is an array. Suppose we create an array of size 5. We have space for exactly 5 elements. Static structures provide advantages such as fast access, simple implementation, and efficient memory organization. But there is also a limitation. What if we suddenly need to store a 6th or 10th element? The structure cannot automatically grow. So, static data structures are useful when we already know the approximate maximum amount of data we need to handle. Now let's look at the opposite idea, dynamic data structures. Unlike static structures, their size can change during program execution. Memory is allocated at runtime whenever it is needed. The best example is a linked list. Imagine a train. If you need another compartment, you can simply add one. Similarly, in a linked list, we can create and connect new nodes as required. This gives us great flexibility. We can grow, shrink, insert, or delete elements dynamically. However, this flexibility comes with some extra overhead because we need additional memory for links or pointers. So, static structures give us simplicity and speed, while dynamic structures give us flexibility. Now, let's move to a second classification, linear data structures. In a linear structure, elements are arranged in a sequence one after another. Think about people standing in a queue. There is a clear order: first, second, third, and so on. Examples of linear data structures include arrays, linked lists, stacks, and queues. In an array, elements are stored sequentially. In a linked list, each node is connected to the next node. A stack follows the LIFO principle, last in, first out, and a queue follows FIFO, first in, first out. So the key idea is simple. Linear data structures organize elements in a sequential order. Now let's explore non-linear data structures. Here, elements are not arranged one after another in a simple sequence. Instead, one element can be connected to multiple other elements. The two most important examples are trees and graphs. A tree represents a hierarchical relationship. For example, think about a file system, an organization chart, or a family tree. A graph, on the other hand, represents network-like relationships. Think about Google Maps, social networks, or the internet. So while linear structures look like a line, non-linear structures can look like a hierarchy or a network. Now that we know the major types of data structures, let's discuss something equally important. What can we actually do with data? The common operations are traversal, insertion, deletion, searching, sorting, and merging. Let's take a linked list as an example. During traversal, we visit each element one by one. For insertion, we can add a new element, such as inserting 25 after 20. For deletion, we remove an existing element. Searching helps us locate a particular value, such as finding 40. Sorting arranges the elements in a particular order, and merging combines two structures into one. So remember, the real power of a data structure is not just about storing data, it is about how efficiently we can perform these operations. And finally, here is one of the most important ideas of this lecture. The same operation can have a different impact depending on the data structure we choose. For example, an array is excellent when we need direct access using an index. A linked list is useful when frequent insertion and deletion are required. A stack is designed around push and pop operations. A queue is designed for first in, first out processing. Trees are naturally suitable for hierarchical data, and graphs are powerful for representing networks and solving pathfinding problems. So, there is no single data structure that is best for every situation. The best data structure is the one that makes the required operations most efficient. And that is the key lesson from today's lecture. Choose the right data structure based on the problem you want to solve factorial. In the next lecture, we will continue exploring these concepts in greater depth. Thank you for joining me in this second lecture on data structures and algorithms. Today, we explored different classifications of data structures and data types. I hope the concepts are now clear. Keep learning, keep practicing, and I'll see you in the next lecture.